Okay, so this will be our last day on section 4.2. And yesterday, every problem that you guys did in the notes and in the homework, the degree of the top was always smaller or equal to the degree of the bottom. What that means is we had horizontal asymptotes. Either horizontal asymptotes at 0 or horizontal asymptotes shifted off of 0, up or down. But they were still horizontal. Yeah, we had verticals too. The verticals aren't going to go away. Verticals are in everything we do. But if the degree in the top is greater, not less than, but if it's greater than the degree in the bottom, then the horizontal asymptotes are going to go away. Okay, so we're going to look at how to graph rational functions where the degree in the top is bigger than the bottom. Now, in general, the quick way you can tell how bad a problem is going to be is look at the degree in the top, look at the degree in the bottom. The further apart they are, the worse the problem is going to be. So if you had like an x to the 10th in the top and an x squared in the bottom, that's going to be pretty bad. That's a 10 in the top, 2 in the bottom, that's a difference of 8. We're never going to really have anything more than a difference of 2, right? So you might have like an x to the 5th in the top and an x cubed in the bottom. It's only a difference of 2. And I'll also do a difference of 1, just to show you that one. So, when the degree on the top is bigger, there's a new thing we can find. This is going to kind of take the place of finding a horizontal asymptote, because asymptotes will not be horizontal today. I guarantee you will have no horizontals. Okay. What you will have is what's called an EBA, End Behavior Asymptote. So I'm going to show you an example, just kind of writing it out in function notation, and then I'll do it with numbers to help it make sense. So let's suppose you had something like, let's say we did 14 divided by 5. Okay. Just going to write the quotient and the remainder. Quotient is 2. Remainder is 4. Okay, just keep that in the back of your head for a second. So when you divide two things, you're going to get a quotient and you're going to get a remainder that satisfies the following formula. Quotient plus remainder over original denominator. And I'm going to show you how that works with numbers, and then I'll actually do one, show you what happens with polynomials. So, my original problem that I did with numbers was 14/5. Okay, I divided 14 by 5. And I'm saying, based on this formula, the answer should be the quotient plus the remainder, which was 4, over the original thing I divided by, 5. That's what this formula says. Is that true? Is 14/5 equal to 2 plus 4 over 5? Yeah. 14/5 is 2 and 4/5 if you wrote it as a mixed number. So that's all that this formula is saying. Your original problem equals your quotient plus your remainder over your divisor. Now, what we're interested here is just the quotient. I don't care about this part at all. I'm going to show you why I don't care about it in the next problem. But I do not care about the remainder at all. If you can find the quotient is the EBA. So yes, we have to do long division. Okay, we learned that last week. But when you do long division, you're not doing anything different. You're doing the same long division, and you're writing down the same quotient. We're just giving the quotient a new name. We're going to call it something different. We're going to call it the EBA now. But all that it is a fancy name for the quotient. Right? So as long as you know how to do long division, you'll be fine with finding an EBA. Right? So let's try an example. Okay, so keep that in mind. Quotient is the EBA. Don't get confused by this fancy new term. It's just a quotient. So let's find the quotient, the remainder, and the EBA when we divide this. What we're ultimately leading up to here is I'm going to graph this by hand. But the first step to graphing something like this by hand is to find the EBA. So let's try finding it. Is this a problem that I could do synthetic division on? Yeah, it's of the form x minus a number. So when I have a choice, I prefer synthetic. I think it's faster. What number goes on the outside? Yeah. 2. And what's going to go for my numbers on the inside? Just be careful, Zach.
2, 4, 0, 3.
Nice. You remember the 0, which that's usually, sometimes people forget it. Okay, so let's divide this out. Bring down the 2. Multiply 2 times 2. Add that column up. Multiply 2 times 0. Add that column up. Multiply 2 times 0. Add that column up. Okay, so the directions are find the quotient, the remainder, and the EBA. What is my quotient? Two.
2x squared.
2x squared, yep. What's my remainder? Yep. 3. And what is my end behavior asymptote?
2x squared.
2x squared. It's the same as the quotient. The quotient is the EBA. And that's what they want. So here's why I don't care about the remainder. All right. So remember the formula I had: quotient plus remainder over original denominator. That's quotient plus remainder over original denominator. That's exactly what I had right here. Quotient plus remainder over original denominator. The reason I don't care about the remainder is, look at that. What happens, remember, end behavior, end means the end, like far away values, big values for x. Look at what I circled. If I plug in a huge value for x, what happens to what I circled? Yeah.
It's just going to go towards 0.
That's going to approach 0. That's why I don't care about it. It approaches 0, it becomes insignificant. Right? Say when x is 1,000,000. If I take 2 times 1,000,000 squared, or I take 2 times 1,000,000 squared and then add 3 divided by 999,998. This is so small that adding it to this doesn't even matter. That's why we don't care about it. That's why the remainder is not important. Because as x gets bigger, it basically shrinks down to nothing. All right. So 2x squared. All right. So I don't know if you've kind of picked up what's happening here. This is an asymptote, 2x squared. What that means is we have a graph that's getting closer and closer to a curved line. So yesterday, you might have had a line like this, and your graph got closer and closer to it. Well, that's getting closer and closer to a straight line. Our graph is getting closer and closer to a curved line. So we actually have a dotted curved line we have to make. That's what makes it a little tricky, but we're not going to graph anything worse than a quadratic asymptote. We're not going to do like cubics, and it gets really hard. So, we already answered this question. What happens to the remainder as x gets bigger and bigger and bigger? The remainder part approaches 0. So we don't care about it. All right, so keep this 2x squared in mind, because what I'm going to do next is I'm going to graph that on the calculator, and I'm going to show you something. Actually, I'm going to graph it in the next example. But before we do that, 3 important points I just want to make. There's a difference between an EBM and an EBA. They're not the same thing. EBM is easy to find. You just take the highest degree term in the top and you divide by the highest degree term in the bottom. EBM is what we did yesterday. I think EBA is harder to find, what we just did, because you have to do synthetic division. We didn't have to do synthetic division yesterday. Okay, today we do. Or even long division. If you don't like synthetic, you can do long division too. Right? So there's a difference between how you find an EBM and how you find an EBA. You will never find an EBA for the kinds of problems we did yesterday. Doesn't make sense. The degree in the top has to be larger to do an EBA. That didn't happen yesterday. For the kind of problems we're doing today, you can find both. We could do an EBM and we could do an EBA. We could do both. The EBA is more important. It tells you more information. So if we were to find an EBM and an EBA for the kind of things we're doing today, they might come out the same, they might come out different. Just find each one of them the way I taught you how to find them. And the last thing I already kind of hinted at, but now I'm just kind of formally writing it down. If the degree of the numerator is smaller than the denominator, this is what we did yesterday. All the asymptotes are straight lines. There's 2 kinds of straight lines we've talked about. Horizontal, vertical. If not, okay, if the degree in the top is larger than the bottom, then what can happen is asymptotes can start to curve. Okay, so again, I already said it, I'm going to say it again. You will not have any horizontal asymptotes with anything we do today in class. None. Okay, so now what I'm going to do is I'm going to graph something. I want to prove that what we just did actually is the EBA. So I'm going to graph the original example 5. I got to go back and look at it. I'm going to graph what we think is the EBA. I know it is. We did it right. And I would just want to look at the picture. Okay, so I need the original problem. 2x cubed minus 4x squared plus 3. If you got anything else in there, just get rid of it. So 2x cubed minus 4x squared plus 3. And we're going to divide by x minus 2. Now, in red, I'm going to graph the EBA, 2x squared. Now, I'm going to do this as a dotted line, just like we normally do when we have asymptotes. You don't have to. I'm just going to make it dotted. So the graph in blue is going to be the real curve. The graph in red is going to be the EBA. All right, so let's set our window. Because I've done this, I know what you have to do. You got to set your Y max to about 30. And you'll be able to see it. So this isn't going to look like any graph you've seen before. It's going to look a little different. But it kind of is going to start to look like a parabola and then do something weird. And you kind of see like the other half of the parabola. Don't worry about what it looks like. All I want you to do is look at that red dotted line. Okay, and I'm going to make that bigger.
How do you make the line dot?
You don't really have to, but if you just highlight the y equals box and hit enter on that, you can change the color and the line thickness and stuff like that.
It doesn't have that.
You don't have that?
No, I think it...
Could be a different option, but that's how you do it on mine. Then you can change it. Alright, so if you look at the graph, can everyone see how the dotted line in red and the line in blue are getting closer and closer as you head to the left? I mean, eventually it looks like they're right on top of each other. They're not. It's just that my screen only has so many pixels on it, and that's how it looks. But you can see they're getting closer and closer and closer and closer on the left, and closer and closer and closer on the right. So it basically looks like a parabola, like if you zoom way out, except there's a problem. You can't plug in 2. If you plug in 2, you would divide by 0. And when we divide by 0, that gives us a what? Vertical asymptote. So basically what you have is a parabola, and somebody slammed a vertical asymptote right in the middle of it. So it causes the parabola to break into 2 pieces. One piece goes down forever, and the other piece kind of curves and goes up forever. This is what we're going to try to sketch by hand now. So, example 6 was just visual. There's nothing to do there. Okay, now let's make our sketch. All right, so things we want to find. Degree in the top is bigger than degree in the bottom. What is the degree in the top?
2.
Yep, Sam?
3.
3. What's the degree in the bottom? 1. What's the difference between 3 and a 1? 2. That means you're going to have a quadratic asymptote. This is the problem we just did synthetic division on. It's the same one. Right? We already know the asymptote. If I remember, was it 2x squared?
Yes.
Okay. So let's sketch that. Easiest way to sketch a parabola is just pick some points. Make a table. If I plug in 0 for x and then do all the arithmetic, what do I get for y? 0. What if I plug in 1 for x? 2. 2 for x?
8.
And let's do 3.
18.
18. Now parabolas are symmetrical. So if I plug in -3, I'm going to get 18. If I plug in -2, I'm going to get 8. So I'm just going to like mirror image it, and then I'll have my picture. Now remember, this is the EBA, so I want to draw this as a dotted line. 0, 0. 1, 2. Notice my y-axis, I'm going by 2s. It's because I don't have enough space. 2, 8. 3, 18. So -1, we'll just mirror image it. 2, mirror image it, and 3. 1, 2, 3, 1, 2, 3. As long as I get everything right. And now draw that in as a dotted line. That's not your graph. That's your asymptote. Okay, so we got the EBA. Vertical asymptote, I already asked Jared about that. That's when you divide by 0. So in this case, 2. So we got a vertical asymptote at 2. Okay, put that in as well. Now, from here, we just need to plot some points. Always check a point very close to the asymptote, so like a value near 2, 1.99, and then a little bigger, 2.01. Let's start with that. So second table, 1.99. I'm at almost negative 3,000. So just before 2, your graph is going way down. Okay, you know what? I'll do it in red so you can see the actual graph. Let's check a point just after. 2.01. I'm way up at 300. Okay, so just after, you're way up here. Now, what did I say yesterday when you draw a graph about crossing vertical asymptotes? Eric? Do you remember what I said?
You don't.
You don't. So those 2 red dots, those are never going to touch. The only way they could touch is if I drew a line across the vertical. No, don't ever draw across a vertical asymptote. Okay, let's get some more points. Let's try, I think maybe like 2.5. That would be a good one. Just barely on the graph. Remember, we're looking at Y1. Y2 is my asymptote. So 2.5, 18.5. 2.5 is like right around here, maybe. I could try 3, but I think I'm going to be off the graph at that point. Yeah, kind of off the graph. 321. So that would be like, that's 20. 1 is like right there. Okay, so I got enough dots in that red section. I can kind of see what's happening. You got to draw it and stay as close as you can to the dotted lines. Okay, so this is going to stay very close. At some point, it turns, and it goes like that. I don't exactly know where that minimum is, but I'm not really interested in getting it exact. I'm just trying to get a decent picture. Okay, now I need a lot more points in here. So let's try 1.5. That would be a good one. 1.5, negative 1.5. So 1.5, and I'm going by 2, so it'd be about there. Let's do 1. That's probably a good one. 1, negative 1. So 1, negative 1. We can do 0. 0, negative 1.5. Okay, so it's kind of doing this weird like turn in there. And now let's do, I think negative 2, negative 3. That should be good enough. So negative 2 is 7.25. Negative 2, 1, 2 is about 7.25. Well, actually, it might be a little higher than that. Right about there, whatever. And what was negative 3? 17.4. You got to pick your values kind of wisely, because if you do too big, you're going to go way off the graph. Like if you do negative 8, you're going to be way, way off. So negative 3 is 17.4. So that might be like, I don't know, right around there somewhere. Okay, so now connect those red dots and see what you've got. Staying extremely close. And then all of a sudden it'll veer away from it a little bit. It's going to turn, go through those dots, and then get extremely close again. And that's basically what it's going to look like. So that red line is getting closer and closer to that black dotted line. Okay, let's just hit graph and compare it to what I got. Yeah, looks pretty decent. So again, it's like a parabola and somebody just slammed a vertical asymptote right in the middle of it. It's basically what happens. That is the trickiest one we graphed today. But any questions on it? It relies on plotting a lot of points. In my case, I did 1, 2, 3, 4, 5, 6, 7, 8. I did 9 points. You might need more, you might need less. It's up to you. Okay, let's look at this one. So, what's the degree in the top here? 3. What's the degree in the bottom? 2. What's that a difference of? 1. This is going to be a degree 1 asymptote. Step down from a quadratic. What do you get if you step down from a quadratic? What kind of equation? Yeah.
Linear.
Linear. What's a linear equation look like? Y equals. Yep.
Mx plus b.
That's exactly what we're going to get here. That's a line. So you might say, well, wait, I thought you said there were no horizontal asymptotes here. It's not going to be horizontal. We're going to have a slanted line. Okay? So that's a difference of 1. You're going to get an equation that's y equals mx plus b. All right. How do I get the EBA? What do I have to do? Think about the EBA is the what? And if you know what it is, that'll tell you what you have to do.
Quotient.
It's the quotient. So if the EBA is the quotient, what do I have to do? Divide them. Can I use synthetic division? No. You got to use long division. But it's only a degree off by 1. So you're not going to have to do a lot of rounds of long division. Basically, you're going to have to do it one time. So you've got x squared plus 2x minus 3 divided into 2x cubed, 7x squared, 0x minus 4. Okay, so Brandon, what's x squared divided into 2x cubed?
X squared, 2x cubed. It's 2x.
2x. There's your mx in your EBA. So we have the mx, we just need the plus b. So multiply that back out. 2x cubed. Eric, what's 2x times 2x?
4x squared.
Squared. And 2x times negative 3. Jacob?
Negative 12x.
What's 2 times negative 3?
Negative 6.
Negative 6. X. And then subtract. That's gone. Zach, what's 7x squared minus 4x squared?
3x squared.
0 minus minus 6. Bring down the negative 4 because it's your next term. It doesn't even matter. We just have to finish up. What's 3x squared divided by x squared? Yeah, Caleb? 3. There's your asymptote. Y equals 2x plus 3. You don't even have to finish that off. If you finish it off, you're just finding the remainder. We don't care about the remainder. So, EBA, y equals 2x plus 3. All right, someone remind me, how do you graph a line with a slope and a y-intercept? What do you do first? Yeah.
Y-intercept.
Okay, so my y-intercept is 3. So what do I do?
Put a dot at 3.
Yep, put a dot at 3 on the y-axis. And now how do I get another point on my line using my slope? Well, say it.
Up to right one.
Yeah, rise over run. Up 2, right 1. Now he said up 2, right 1. I could go down 2, left 1. It's up, whatever. Did I mess up? No, I think I'm good. Okay, so draw that in. It's better if you use a ruler, but I kind of did okay. So that's my slant asymptote. All right, what else did they want? The EBA, so in this case, the EBA is what we call a slant asymptote. I'll write that in a minute. And the vertical asymptotes. Okay, vertical asymptotes are, what do you have to do to make those easier to find? I mean, some people might be able to see them right there, but I would do something to the bottom there. Yeah, factor it. Okay, so let's factor it. And Emily, can you tell me how the bottom would factor? Yeah, perfect. So x squared minus x plus 3 is plus 2. Perfect. So what are my vertical asymptotes here? Yeah. Yeah, and 1. Negative 3 and 1. Now, is everyone okay if I erase some of that long division because it goes over my graph? I need this space right now. All right, so we got negative 3. 1, 2, 3. That just keeps going. And positive 1. So it's kind of like the problem we did yesterday, where we have 2 verticals, except instead of having a horizontal, we got a slant. That's all. Okay, so now we're gonna test some points on each side of the vertical asymptotes, very close to these numbers, a little bigger, a little smaller, and then we'll maybe check a few other points and see what we got. Okay, so first thing, I need to type it in. So we got 2x cubed plus 7x squared. I'm kind of just editing what I already had. Minus 4 divided by, I just need to fix all that. X squared plus 2x minus 3. Okay, let's go to our table. What's a value that is a little bit smaller than negative 3 that I could type in? Well, you care? A little smaller than negative 3.
Negative 2.999.
That's bigger, but we're going to do that one next.
It's going to be like negative 3.001.
Yeah, so that's a little bit smaller. And we're at positive 1,000. I'm going to type in the other one she said at the same time. And we're at negative 12,000. So just before negative 3, way up high. Just after negative 3, way down low. Now, are those green dots ever going to connect? No. One's on one side, one's on the other. They can't. So you got 2 different sections happening there. Let's check 1. Value a little smaller than 1, like 0.999. Okay, and we're down at negative 1,000. So way down here. A little bit bigger than 1, 1.001. Positive 1,254. So way up here. So, by looking at where my green dots are, can anybody tell how many sections I'm going to have in this graph? 3. It's going to be 3. Yeah. You can start with any section you want. I would start with the left. I need more data though on the left, so I want another point or two. What would be a good x value to plug in that would be in the left section? Yeah. -2 is going to be in the middle section. It's a good value, but not for the left section. So when I think of sections like this is the left, this is the middle, this is all the right. Those verticals kind of separated into 3 parts. Yeah, you want to give me another one? Yep, I think -4 would be a good one. -4, -4. Okay. 1, 2, 3, 4. 1, 2, 3, 4. Now, just because I've done this a lot, I have enough information, I think. Connect those 2 green dots and just stay very close to the dotted lines as long as you can. So it stays very close. Starts getting away from it a little bit. It's going to curve and get closer and closer and closer to that. I think that's what the left section is going to look like. Now, Brianna said -2. I think that's a good point for the middle. -2, -2.7. 1, 2, 1, 2.7. What would be another one? Another good point in the middle. Jared?
0.
Yeah, I think 0 is a good one. 0, 1.3. And now for me, I got enough. I can see 4 dots in the middle. Connect them and just stay near all the asymptotes. So stay very close. It's going to move away a little bit from that one. Start following this one. And then curve. And get very close to that one. So that middle section almost has a very straight part. I think it's going to look pretty straight in the middle. And now, what would be another good x value for the right section? Zach? 4. We can try 4, but I think it might be, yeah, I can just barely get that on the graph, maybe. 1, 2, 3, 4, 10, 11 would be like right there. Let's do one more. Yeah.
3.
Yeah, I think 3, 2, 2.5. 3 is 9.4. So maybe about there. I am going to do, I can't do 1. I'm going to do 2. 2, 8. 2, 8. Okay, that gives me a pretty good idea. Connect all those green dots and just stay close to the asymptotes. Just like that. So let's hit graph and see how we did. So here's the left section. Let's see if it starts to curve up. Kind of a gradual curve, yeah. That middle section that gets pretty flat. And then the right section that we have that little part. Yeah, perfect. What would be the range of that? Think about drawing a horizontal line and moving it up and down. Would it ever miss anywhere? No. If you didn't have this section on the left, then I would say yes. It would miss everything in here. But that section on the left takes care of it. Yeah. Perfect. Okay. Any questions on that one? Okay, so last one we're going to do, you don't have to sketch anything by hand. I just want you to type this in on the calculator and tell me what you see. Just want to see what that looks like. So, let's type it in. And we've got 2x to the 4th plus 7x cubed plus 7x squared plus 2x divided by x cubed minus x plus 50. And we'll start with standard window. Now, look at the difference between the degree and the top and the bottom. What's the difference? 1. So I'm expecting a degree 1, or what's called a slant asymptote, like we had. I'm not seeing it. I don't really see how you could put a line in there and have a slant. Like I can see like on the left there, it looks like it's getting closer and closer, but on the right, it looks like it's almost going straight up. So what I want to do is set my Y max a little higher. Okay. You know what? Let's set the X max a little higher too. So X max to 20. And let's set the Y max to 30. I'm going to hope that that second part starts to curve back. Did it curve back? What do you think? Does it look like it's starting to bend back a little bit? Yeah, I think it is. So now I'm starting to see that, okay, there probably is a slant asymptote, and it's like right, this isn't perfect, but it's kind of like that. If I zoomed out more, I could see it even better. But I can now see that it's getting closer and closer. Okay, so I would say, as far as finding a complete graph, that's a good window that shows you the big picture. Okay, so I'm going to just put this, actually I'm going to put this over here. I think that was -10. So this is good for the big picture. X min and max, Y min and max. Is there anything in that graph that looks maybe suspicious, like we might want to check out a little more?
The bottom.
Yeah, what about the bottom part?
Kind of looks like it's also gonna.
Wait, which bottom part are you talking about?
Like the very, very bottom left.
The disconnected piece?
Yes.
So, alright, we could check that out if we wanted. We could go like, we could set our Y min at like -40 and look further down. But you're not going to see anything else interesting happening there. This part's just going to continue down, and that other part's just going to continue left. What else there, though? Does anyone see something else that you might want to zoom in and check out a little more and see what's happening? Yep.
Is there another asymptote?
Yeah, there is a vertical. So there is going to be a vertical right in there, and you're going to have a slant. But that's it. There are no more asymptotes. Anyone see something else I could zoom in and check out a little more? Something there isn't as it seems. It's because we're zoomed out so much.
Maybe the flat part?
The flat part. The flat part. Okay, remember we said flat, right? Okay. Let's zoom in on that section. So what I'm going to do is I'm going to go from like 2 to -4 on the X, and I'll go -1 to 1 on the Y. So -4 to 2. And now I'm zooming way in. -1 to 1. So we're not looking at the big picture. Now we're zooming in to see what's happening here. Okay, what does it look like is happening there? Yeah.
It's going a little under 0.
Looks like it's actually crossing the axis, like we have a root. Right? We can't tell because we're not quite zoomed in enough. So let's zoom in even more. Right? Instead of going -1 to 1, I'm going to go like -0.1 to 0.1. Okay? And take a look at how that would look. All right, so let's go even more. And remember, how did you describe this, Jared? You said it looked originally flat. Okay. So let's go -0.1 to 0.1. So now we're zoomed way in. And look at what this actually looks like. Thank you. Bless you. So, what originally looked very flat is actually a W shape. So this is the kind of graph where I would call that hidden behavior. Because if I said to you, tell me where this graph crosses the axis, you might look at it in the big picture and say, nowhere. It just looks like it's right along the axis. It's not right along the axis at all. It actually crosses 4 times. So, I don't think you can describe a complete graph with a single window. I think you need a window that shows you the big picture so you can see the slant and the vertical asymptote. And then I think you need a separate window that shows you what's going on in that flat part. So I think you need both of them. So this would be kind of a zoom in window. Okay, you really need both. There's no way to see all of this at the same time on the same screen. Okay, so big picture window and then a zoom in window. Okay, so that's it. The whole point of that one is just make sure you look for things either on the screen or off the screen. Off the screen is harder because sometimes you don't know where to look. But at least try to look for things that are hidden. Okay, so homework for tonight, same section as last night, 235. It's 40, 41, 45 to 47, and 51 and 55. So I think it's like 6 or 7 questions. Okay. Again, reminder, I will be after school tomorrow if anyone needs extra help. If you have anything to get done, remember end of term is this week. So this is your last week of academics. Just make sure you come see me to finish up, turn in whatever you got to do.